Okay, and I'll just put the link to the meeting. Perhaps someone download the link. Okay, okay. So all is well. Yeah. All right. Not too many people awake, but anyway, let's get going with the stubborn broadcast. So last time we looked at first the regular or the first best effort broadcast, then the reliable or regular reliable broadcast, and then uniform reliable broadcast, and now we can see the stubborn broadcast approach. So this is in a fail stop, crash stop process. Processes can be crashed or stopped, and it's a fail silent environment without which is without a fail detector. So what's the significant thing here? We have when you see this, then the first thing you must remember that if it has the stubborn name, it means that the algorithm is sort of a stubborn in that it keeps trying. So this is the property number one here. If a process that never crashes broadcast message M, then every correct process delivers M an infinite number of times. Because remember that we had the stubborn link, which was a link abstraction that kept sending the same message over and over again. And it's a similar thing here, only that now we are talking about the broadcast. So if you remember from uniform reliable broadcast and even reliable broadcast, yeah, we had this property number two here, no duplication, no message is delivered more than once. Now with the stubborn broadcast, we do not have this. So if you see the description here, there is the property for no duplication is missing. Anyway, it's the reasoning why it doesn't have the no duplication property can be seen here, because remember the regular regular reliable broadcast and the uniform reliable broadcast, they use point-to-point links, but here we are using stubborn point-to-point links, and this link abstraction doesn't have any duplication removal or filter. Then there is another broadcast abstraction in the crash recovery abstraction. So what's new here is definitely the property 1. If a process that never crashes broadcasts a message M, then every correct process eventually delivers M. So we can see the algorithm for this here, that when the application layer triggers the broadcast, it's sent, the message is sent to all the processes, and when you receive a deliver message back, or your process delivers, then you check if you already delivered this message from this process, and if not, you store this to your hard drive or stable storage, and you trigger the delivery event further up the stack. But since we are now in the crash recovery abstraction, we also have the recovery event, and then we are able to retrieve the delivered set from stable storage when we recover from a crash. So this thing here, it suffers from one design flaw, but maybe we will see it even more clearly on the uniform reliable broadcast. So remember this. Oh, we can actually see it maybe best here. So remember that a process can crash at any time. So it can happen between execution of functions or events, but also inside the execution. So with this particular algorithm here, you have the, for example, you can imagine that the sender crashes halfway through this loop here, and this would cause that only half of the broadcast messages are sent out, and thus only half of the processes would actually deliver the message. But it's also possible that you can, for example, if these two events are like the store function here, like storing to stable storage, and the trigger up the stack, if they are running concurrently, then you can, it's possible that you can, for example, crash in the storage part of the algorithm, but you deliver this anyway. So there's many, there's a, this algorithm is, because of this, it's a best effort type algorithm, that it doesn't have any strong guarantees that the broadcast will actually be received by all the other processes. And then, but then they have the uniform reliable broadcast, which has the same properties, but adds the uniform agreement, which is, if you remember from just uniform reliable broadcast, it's also, or yeah, if a message M is the log delivered by some process, even if it's correct or faulty, then the message M is eventually delivered by every correct process. And this means that if a faulty process broadcasts a message, then only if a sufficient amount of other process receive this message, it will be actually delivered. So we can see the algorithm here, and well, the most interesting things here, it's on the deliver event. So on the last if statement here, there is a check if when you receive a broadcast message from a process, then what you do is that you check if you already sent an acknowledgement for this process. And if you didn't check, then you add it to the set of acknowledgement messages that you have sent. And once you have, or the cardinality of the set of acknowledgement messages is above n divided by 2. So this n divided by 2, remember, this means the number of processes in the system. So this part here, it means that you have a majority of processes, like you have received acknowledgement from over half of the processes in the system. Yeah, and then there's a check that you didn't already deliver this message, and if that's the case, you deliver this message. So these things there with majority, you need to be familiar with these things. Also, when you will, when we will go into Paxos and different consensus algorithm, it's crucial. So yeah, the thing to keep in mind here is that when you are talking about the crash abstraction and also the Byzantine abstraction, we have the F, and F is the number of faulty processes that we can tolerate. So anytime we are discussing the consensus algorithms and also these algorithms, you need to always keep these two numbers in your mind, that n, it means the number of processes in the entire system, and f is the number of faulty processes. All right, so now we will go into the more interesting, useful things, perhaps, with the probabilistic broadcast and yeah, reliable broadcast. They use this acknowledgement messages, so to agree on which messages to deliver. When a sender is sending his message out, then the other processes are replying back with an acknowledgement message that they have received this broadcast. So you can imagine that this is like all-to-all kind of message exchange that first the one process is sending the actual broadcasting the message you want to broadcast to all the processes, and then all of the processes are again sending an acknowledgement to everyone else. So this works fine when you have 10 processes or so, but if you have thousands or millions, the system can no longer handle the this acknowledgement transmissions, because there are simply too many, and this is a very fundamental, let's say, scaling issue, and this is why that there's been there is a different approach to reliable broadcast, and it's by having just a probabilistic broadcast, which have a different have different guarantees, because now we are only providing probabilistic guarantees that let's say usually and most of the time, then the message will be broadcast to everyone, but there's not a strong guarantee for this. Yeah, so here is an illustration of the broadcasting with reliable broadcast, that the first process is sending his broadcast message to all the different processes, and then all of these receivers here, they should acknowledge to everyone else that they have received this broadcast. So it's a n squared message exchange, and a different approach is to use a hierarchical type abstraction or topology. So the sender will send to two different ones, and then each of them relay this down to two different ones, and then to two. So it's kind of a binary tree here. But the difficulty with such a structure is that if one of these higher level nodes have crash, then everyone that's underneath will not get the message. So you have a kind of correlated failure scenario here. Whilst in the example A, then if one of these crashed, then it will only concern himself, not everyone else. So yeah, this type of probabilistic broadcast, for example, in streaming applications or voice applications, where you don't need to have a strong guarantee that everyone receives the message. Yeah, so then have one example from probabilistic broadcast. It's what they call a epidemic dissemination protocol, or a gossip protocol, and it's kind of similar, or draws inspiration from a real epidemic. Then with first there is one individual that's infected, and then this individual, he affects some others, and this step number 1 and number 2 keeps going on until the some period where the whole population is infected. So here's the module description for a probabilistic broadcast algorithm, and you can see properties number 2 and number 3. They are well known from deterministic broadcast algorithms, but now we have not a strong validity property, but we have a probabilistic validity such that there is a positive value epsilon, such that when a correct process broadcasts a message M, the probability that every correct process eventually delivers M is at least 1 minus this epsilon. So obviously you want to keep this as close to 0 as possible. So one algorithm where they do this, it's called the eager probabilistic broadcast. And again, remember the difference with the eager and the lazy algorithm. So this eager algorithm, what it does is when a process gets the deliver event or the broadcast event, sorry, with some message, it adds it to its own deliver set, and then it triggers the deliver up against the stack, but then also it runs this function, the gossip function. So the gossip function, it it's taking a subset of processes, and the function is up here. So this pick targets function, it says it returns a set of processes. It actually probably should be the capital P here, if you remember, which the capital P means all the processes in the system. Anyway, what this does is that you define how many targets that you want, the K parameter, and you just run the random function, and if a process is selected, then you add it to the set and you return this subset. So everything depends on this random function, meaning how likely it is to pick a candidate and how many that you want, which is the K. And it doesn't say here, but you can infer from this algorithm that it's not possible to choose the same number again. So it's what do we call it? Without replication. This random function. So yeah, then you have a number of processes that you randomly picked out, and then you send a message to them on the fair loss point-to-point links. And one more thing that's important is that you when does this whole thing here terminate? And the termination is controlled by this R parameter here. So whenever the fair point-to-point link deliver a message, it will trigger gossip again, but every time it triggers the gossip again, it will decrease this R here. And this is how many rounds will this run. So for every round, you pick out K processes, and you run this some number of rounds. So if we had the assumption that this random function was such that you would not pick the same process again, then we could calculate what is the maximum number of rounds or K that you would need. Yeah, so here is an illustration of this algorithm with yeah, both K and R set to 3. So the K is also called the fan out variable. So the process that sends the broadcast, it's sending the broadcast to 3 different processes, and all these 3 that receive the broadcast, they are sending to 3 new ones, and again those 3 they are sending to 3 other ones again. So in the end, you yeah, in this case everyone got the message. But also one thing here is that, for example, the process number 1, in this case, he got this message back 2 times, which is kind of redundant messages exchanged. So yeah, so one thing to note here, it's that how many processes that receive the message for each round. This is the K parameter, and if we have a very large K, then more processes will receive the message, and we also the larger the K is, the less rounds we need to have some probabilistic guarantee that all processes receive the message. But it's actually what we are trying to solve with this probabilistic broadcast is to have a lower K. So it's obvious that if we set the K to the same number of processes in the system, that then all the processes will get the message, but then we have a very high load on the sender especially, and also the receivers if they have to send acknowledgement messages. So there is also always a trade-off that you have to make here to set the correct values for K and R. And some different values for R and K can be seen in the book. I will not go into details of what they mean here, but we can see here like that one approach it reaches probability 1 in maybe 4 rounds here, whilst the other approach it seems to cap out at 0.9 maybe. So or maybe it will keep going until 1, but anyway, such graphs and illustration as this is very useful for your paper or project. So that's something to keep in mind. Yeah, and I mentioned that there's a lazy approach also. So usually when you have an algorithm that says that it's eager, then you can expect to find a lazy version. But yeah, as we saw, the the eager version, it just whenever it gets the broadcast, it's immediately broadcasting this message out, and this causes a lot of resource consumption because there's a lot of redundant messages. So one approach is to only do the push message style in the initial phase, and afterwards switch to a pulling type approach, where the process will try to pull down whatever message they are missing. But obviously, it can be kind of strange to how will you pull down a message from a different process if you don't know that it exists in the first place. So how can you make such an algorithm? But we will see here. So I think this algorithm is actually so large that it's in 2 pages, but let's see. The main thing here. Yeah, it's kind of similar to the eager approach in the gossip step here, or this gossip procedure, that it has the pick targets, a number k, and then it triggers the fair loss point-to-point links layer. But in the deliver event here, it does some step further down here on the last last lines here, which is it's checking that if it's missing any messages in the whole set here, then it's doing like a gossip request for the message. So it's, if it detects that it's missing a message, it will send this request out to the rest of the network. And also there's a timer here, so that it waits for some period of time until it will go to the next round, let's say, and then it can kind of know what messages or it missed, what messages it's missing. So actually, I kind of wanted you all to have some training in studying this kind of algorithms, because this is very relevant for you for your project, because in the project, this is a typical thing that could be described in the paper, and then you need to be able to kind of extract this information, which is can be a bit compact. So here I have written down 2 questions for you with these 2 lines here, and yeah, the first question the first question is that can you formulate or say in a few words. What's the purpose of this thing here? And also the second question, it's yeah, what are the assumptions here? So inside this whole if else if statement here, as I said, it's checking that if you're missing any messages, and if it detects that some messages are missing, then it will send the gossip request. But there are some underlying assumptions here that it's very, if you had to describe this algorithm, then this is one thing that the reviewer would expect that you would be able to answer. So yeah, I think that if we just take, for example, 6 minutes, 5-6 minutes break, and then just think about this, and if you want, you can just write in the chat if you already know, or if not, I will explain to you what I would expect you to write about this. So let's continue in 5 minutes or so.
Recording in progress.
Okay. So, who wants to go first? No, I'm just kidding. You can just be silent if you want. Yeah, it's very important that you're able to analyze algorithms if you're asked to review papers to evaluate what are the benefits and disadvantage with the different approaches. But for the question number one, how what answer that I would accept, it's it must be something that you're able to formulate a statement about load balancing. So you must be able to say that this function or this if statement here, it does so that the system is only storing some of the messages, or you can also say that only parts of the processes in the system are storing the messages. So it's not clear, fully clear from this short function here if it's so that you're putting the stored message or to your stored set on a probabilistic approach. For example, if this alpha here was 0.5, that you would put only half of the time we will put the messages into the stored set, or if it's so that this alpha depends on the let's say your identification of your process, so that if you are some specific process, then you will put this into your stable storage. Okay, and so the question number one, something you must formulate regarding load balancing. And for number two here, what are the assumptions here? The assumption that I was looking for here is that this algorithm will only work if it keeps sending new messages. So if, for example, you wanted to have this whole abstraction probabilistic podcast and you only sent one message, then this thing would not work, because it would never detect that it's missing some messages. So that's I don't know if I can move this. Yeah, so that's what I was looking for here, that you were able to see that this algorithm, it will only work if we are assuming that there will be let's say an infinite number of messages, that you can only detect a message is missing if you receive more messages in the future. All right, so okay, now we will go into next chapter, FIFO and causal broadcast. And FIFO, this means first in, first out. I think, unless probably there's some other wording for this abbreviation, but anyway, the point of this chapter here, this is to say something regarding ordering of messages, because remember, reliable broadcast, it didn't tell us anything or have any guarantees about the actual ordering of the messages that was received. So this is of course very crucial, because you can just imagine with the mathematical operations or arithmetic operations that it has some significance if you do the multiplication first or the addition first. So you're not free to change the ordering of these things. If you do that, then you will have a different answer. So this is why that in a fully consensus reliable system, it's very important that also the ordering of the messages are preserved and all the processes are executing the commands in the same order. Because if they do not do it in the same order, then, as I said with the arithmetic example, then they can easily become out of state. So if you do, if you have let's say 5 multiplied by 5 plus 5, so 1 is 5 times 5 is 25, plus 5 is 30. But if you would do 5 plus 5, it's 10, multiplied by 5 again, it's 50. So just very basic things, but if you have hundreds and thousands of commands, the system can be totally out of state by these things. So this is why we need message ordering. Yeah, and then I just want to show you in this. This is an example of what would happen in a reliable broadcast approach. That the P1 and P2, they are processing the M1 message first, but the P3 is processing the M2 message first. So clearly then this system would be out of state from this execution. Yeah, and module description here. It's borrowing from the regular reliable broadcast with the added property FIFO delivery. If some process broadcast message M1 before it broadcast message M2, then no correct process delivers M2 unless it has already delivered M1. So so remember that one thing to be very clear about is that this FIFO property, it only gives a guarantee about the cases where one process is broadcasting both of these messages. So if the same sender is broadcasting both M1 and M2, then with FIFO delivery, you are ensured that all the processes will deliver them in the same order. but it doesn't provide you any guarantee if there are many senders, broadcasting concurrently. Anyway, let's not go into the most complicated cases at once. So here's the algorithm. It's using this. Anyway, by the way, if you have any questions regarding these algorithms, because maybe I go too fast or too slow, just say, and I can adapt to your needs. Basically what this FIFO abstraction does, it's putting the message that you receive into a pending set, and it's like on the event that you receive something that's not in order. For example, you can receive a message that's like each message is now attached with a sequence number, and if you receive some message that's 2 or 3 messages ahead, then it's simply added to this pending set, and whenever this message that you received, let's say from the future, is the next one to process, it will be processed. It will be removed from the pending set, and you will increment your next counter or sequence number by 1. So this is basically how it works, and with this abstraction, we are now guaranteed that if M1 sends both, if P1 sends both M1 and M2, they will be in the same ordering. But as I mentioned, we still don't have a guarantee for what happens when there are multiple processes broadcasting. So in this case, we have the situation where P1 is sending M1, and but also there's a P2 that sends P2, and it happens so that P2 is sending M2 directly after processing the first message, and somehow it ends up at P3 before the M1, and it's causing the P3 to be out of state with the system. So this is clearly not a good state to be in. Then we have, let's see here, don't skip anything important. Yeah, let's go into the next thing, causal order. With what we call the causal order or causal order, I'm sure you can pronounce it better, but the point is that now we are having some stronger guarantees when it comes to cause-effect relations or happen before relations, that we can say something about what messages happened before the other ones. So we have three let's say different cases where we can say this. That is obviously like with FIFO, that the same process broadcasted M1 before M2. Then it's easy to say that M1 happened before M2. Then we had what we saw kind of in the last slide, where the message M1 was Yeah, actually, I've seen I have one typo here. I will fix for you. So it will be. I think it should be like this. So that the message M1 is was delivered by. No, it was correct. Sorry, I was reading my own slides here. But yeah, here it says that yeah, if it's delivered by one process P, and then this process P is broadcasting a new message afterwards. And then the third case is that there's some intermediate message, what's it called, M prime, such that yeah, M1 happened before M prime, but M prime happened before M2. Then you will be able to use this intermediate message to say something about that M1 was before M2, or M1 caused M2. But so here are the three cases that we can definitely say something about ordering. That if it's the same process that's sending both messages, then we can just look on the timeline and it will be clear what's the ordering. In the second case, we can say that M2 was after M1 because M2 was only broadcasted after M1 was delivered. And in the third case, we can extend this to use the M prime as the intermediate event, because yeah, M prime was broadcasted after M1 was delivered, and same thing for M2, it was broadcasted after M prime was delivered, and thus M2 must happen before M1 must happen before M2. Yeah. So so here it's building on the regular reliable broadcast, but now instead of FIFO delivery, we have a cursor delivery for any message M1 that potentially caused a message M2. No process delivers M2 unless it has already delivered M1. So when it says potentially caused a message M2, it's more that it's put like I just think about it that M2 happened after M1, not necessarily this caused thing, because it kind of in some sense sounds that M2 was depending on M1, but it might not always be the case. But that's why it says like potentially, because in some cases it is not depending on M1, but it could have been based on the ordering that we have. So what's this? In the same slide. Yeah, and then they have the same thing with the uniform broadcast, uniform reliable broadcast. So algorithm here. Yeah, what happens? What does it do to preserve this ordering? So they have kind of two approaches that you will see. One is called no waiting, and the other one is well, it's not called waiting, but it kind of is waiting. But yeah, the thing here, the main point here is that you are always appending the past messages to the new messages that you're broadcasting. So whenever you are whenever you have a broadcast event from the application, you are triggering the reliable broadcast, but you're in addition to the data that the application wanted to send, you are adding the past, meaning all the past message that was sent. And this obviously sounds a bit crazy, but anyway, this is one way to solve this problem. That now what you gain is that if someone didn't receive one message from a different process, then it can be received by another one. So whenever you receive a message, you when you deliver a message, you check if you already delivered it. So first is the no duplication property, and then you check the whole past. So you check all the extra messages that was appended to this message, and you check if there's any one of them that you didn't already know about. So if you didn't know about them, you will deliver them, and yeah, you will basically add them to your own past so that you can send them to different processes later on. Yeah, and yeah, as I mentioned that the main problem with this approach is that it's kind of poorly scalable because your size of the message, it will just keep on growing indefinitely. So it's not a practical algorithm in that sense. So obviously what we will do is to optimize this part where we are appending all the messages that was from the past. But the execution flow, it looks like this. And now we see that P1, it's sending the message M1 to 3 processes. And we're sending to all 4, but the 4th message is very, very delayed here. And then after receiving M1, P2 is broadcasting a message M2, and it's appending the message M1 to the message flow, to the message itself. But obviously, all of these P1, P2, P3, they already know about M1, so they will just discard that. But P4 didn't know about M1, so he will first process M1 and then M2. And then when finally he receives M1 from P1, he will also discard it because he have seen it before. And this slide, it's showing the same thing, only that now it's from the book. So I guess it's not so interesting to see. But then to the approach to fix this, with ever increasing message size. It comes here with in the form of a garbage collection of the past. So what it does here, the main thing is that on the last event here, saying that when the message has been or you have received acknowledgement from all the processes, so that all the correct processes are in this set, then you can remove all the messages that all of them have seen. So this basically mean that you can prune whenever all of the processes have seen a message. So that's this algorithm. I'll not go more into this one because it's basically just an optimization to remove the past, but kind of the more interesting is this one, because here we have the notion about vector clocks. And remember I talked about a logical clock. A vector clock is just many logical clocks. And it's this V here. So V, it's initialized as 0, 0, 0, 0, 0, 0, 0, 0, depending on the number of n, which is however many processes you have. So first, the time for all the processes will be 0. So it's like a sequence number. And there is a rank function down here. And this rank function, it's let's say a way to go from the PI, the process index, or to the array index. So it will be obvious to have like a process number 1 is position number 1 in the array, and the number 2 is number 2, and so on. But this rank function, it just captures that you can have an arbitrary ordering of the array if you so like. Every process is keeping this vector here, a vector clock, and then they are attaching this to the message when they send here. So whenever the application is triggering a broadcast, then when you go further down the stack, you are adding this vector. So what's the advantage here? Yeah, or you kind of get the same result as the no waiting algorithm, but now we no longer have to carry the whole past itself. We have like a constant size of the message, which is just this added vector clock that we added instead. So this vector clock, it's represented by this four element array here, and each element in the array, it's the clock of one of these processes. Yeah, one thing maybe I forgot to mention here is that you can only casual order broadcast deliver once you have delivered all the missing messages. So you only do this. Yeah, you must process all the missing messages. So here is a drawing of this execution. I hope you can see it. But the process P1 here, it's sending a first message and it's increasing its vector clock. And all the different processes that get this message, they're also increasing their vector clock. When P2 is want to send a new message, it's just increasing the second element in the array because it's the second process. And then here we see that the process P4, it gets the message M2 first before it gets the message M1, but it will not deliver it because it first must deliver all the missing messages that it can expect to have. So it knows that since it's clear that two messages have been sent, so it received in this message here, the vector will be 1, 1, 0, 0, but upon receiving this, it knows that it has state 0, 0, 0, 0, meaning that this is actually the second message that it received first. So it will not do anything until it gets the first message, and only then it will deliver them. So this is why this is kind of waiting until it receives the message, until it do the processing. So it's using this pending set. All right. So we are very, very fast. So perhaps we can do take just 15-minute break. Yeah, okay, we have one question first. When the process on the receipt message, they let's see. When the process up on received the message, they didn't update their clock. So is there some message that didn't update their clock? Or because here they are this VC, this is the vector clock. It's updated for all the process, and maybe you didn't see this one down in the corner here, but they have all the same. Now they have all the same clock. Yeah. Did you get the? Okay. Yeah. So okay, one thing to be very very clear about in distributed system is that we don't have a global clock. So always this variables that we it's described here, and here they are local, only local to the process itself. So this is why that uh, uh, at any point in time, all the processes might have different views on what is the correct time or what's the correct clock. So process number 2 is he's the first one to update his clock already at this time, and when P2 has this clock, then P4 has only 000 in his clock. So every process can have a different view on time. Okay, but yeah, if we do 15 minutes and break, and afterwards we can go through this chapter, which is the last one. Or there's actually 2 left, but they are pretty similar. So if we continue from 10:40, then we will do the rest. Okay. Okay, are we ready? In 15 seconds. Okay, let's start. Any questions so far with anything? um, if not, we will continue to Byzantine faults. Remember Byzantine faults. This means that the process can behave arbitrarily, deviate anyway from the algorithm. It can pretend that it's working or is correct, but actually it's not, and we need to really be careful when thinking about this, because it can deviate in any place in the stack, from the lower level message exchanges all the way up to the application layer, or one level below the application layer at least. So it can be both malicious, meaning that there is some entity trying to control the system in a bad way, or it can be due to a hardware failure, for example, or a network failure, or anything really. So, but the main thing is that we want to design algorithms that are so strong that they can allow some parts of the processes to deviate in any possible way. So one typical idea is that hey, let's just add the signatures, or the digital signatures to the messages from the reliable broadcast, and if we use signatures, and then we know for sure that no one can fake messages, because only the one with that has the private key can sign the message, and there is no feasible way to try to derive the private key from what is public knowledge. But the thing that this idea doesn't account for is that the sender can send multiple messages, or especially conflicting messages, and we saw an illustration of that in the introduction to Byzantine failures. So previously we saw on the FIFO and the coastal ordering that we only added like a vector clock, or some kind of sequence number. But with in the Byzantine case, it's not so simple, because we cannot simply just trust this tag or clock any longer. So in the Byzantine, whenever it's a Byzantine, we need to think about a Byzantine quorum. So yeah, I wrote down what's a Byzantine, or what's the purpose of a Byzantine quorum. So the purpose is that whenever we have two of them, you know that there must be at least one process that is correct. So that's the That's the idea. And a Byzantine quorum, this is any set that's larger than n plus f divided by 2. So remember, n is the whole system, and whole, not the whole system, but it's like all the process, the number of processes in the system, and f is the how many failures that you tolerate. So if you have such a large subset, then this subset must have n minus f, because there was n plus f. So if we subtract that, yeah, we should, yeah, so we should, if we subtract f from n plus f divided by 2, it will be n minus f divided by 2. So I hope you are clear on this arithmetic. So if you combine two Byzantine quorums together, you now have n minus f correct processes, and yeah, it says larger than, so now we have more than n minus f correct process, but in our initial definition, there was only n minus f correct processes. So this means that it's not possible to have two Byzantine quorums without there being overlap of some correct processes. So I hope that's clear. Anyway, yeah, so here we have one abstraction for the what they call consistent broadcast. And if you see here, we no longer have any agreement property. So this actually doesn't provide you with any guarantee among the correct processes, and we can see why in the algorithm itself. But it has other nice properties. Yeah, the validity property. If a correct process broadcasts a message M, then every correct process eventually delivers M, message M. And the integrity check, which is something that you will always run into whenever it's a Byzantine fault system, or it's tolerating Byzantine faults. So integrity, you probably heard about this from if you took like a security, data security course, but it means that the message cannot be modified, or if a process is trying to modify the message, it will be detected. But in this definition, it says that if some correct process delivers a message M with sender P, and P is correct, then M was previously broadcast by P. So, but for me, it's not so obvious that this is what they want to say here, that we cannot modify the message. Yeah, and then consistency. If some correct process delivers a message M and another correct process delivers a message M prime, then M is the same as M prime. So here it says that this abstraction, it allows one message to be sent in one instance. So this whole thing, it's only designed, or it's only designed to send one broadcast in one instance. So the algorithm here relies on two phases. One is the send phase. I don't know if it doesn't say the events here, but it's like one send phase, and afterwards an echo phase. So first the process is sending the broadcast to all the processes, and then they are echoing this among themselves. So the echo, it's all-to-all communication step, but we can see here that whenever the application triggers the broadcast with the message M, what happens is the same thing as we saw in most of the other broadcasting abstraction, that simply iterates through all the known processes and sends sends the message on the point-to-point link or the authenticated perfect point-to-point link. So then there is two types of delivery event. There is one delivery event, but there's different handling depending on the message that was received. So one is if you receive a message send, and the other one is the echo thing. But if you check the send first, so send event, search. So so here this is only for the process S, and so the process, your own process will send the echo to all the other processes as well, and when they receive echoes, adding to the echo set, and whenever you have received a majority here, a large enough Byzantine majority, then you will deliver this off the stack. Just the so here the n plus f divided by 2. This is well, if we do the I try to do this calculation here for you, if you remember, but N plus F divided by 2 is a Byzantine quorum. But also, if we expand this out, we can do this here. Kind of easier on a black board, but if we have n plus f divided by 2, this is equal to let's say 3f plus 1 plus f. Well, we can, if we we can also say yeah, we can do so. 3f plus 1 plus f divided by 2, because remember n is greater than 3f plus 3f, or n is greater or equal to f plus 1. And this I can put such arrows, maybe it's maybe more correct. Yeah, so 4f plus 1 divided by 2, and in the end we have 2f plus a half. So then if we will do so if we have we can sort of have so from this thing here, I hope that you will see that if we have n is greater than 3f or greater or equal to 3f plus 1, and we have this Byzantine form here, and if we write it out, it will be 2f plus 1/2, which means that this thing here must be greater or equal to n minus f. So meaning that we have a quorum of correct processes. So that's what this step here. So that at least we have so many processes has replied to us, and we were able to verify the signatures of these. Any questions regarding this? So the execution looks like this. We have the send step, and yeah, I think I messed up this one is the one we are looking at now. Yeah, but this is the execution. Yeah, here we go. Yeah, so this is the execution of this. We have the send, the echo phases, the communication steps. The send is sending the message to all the different processes, and the echo, it's echoing to the rest of to the all the other processes. So it's a first it's a n communications, and then another n for each n. It's another n, meaning that it will be o, big O of n squared communication. And here it's missing the echo from Q to R. So for some reason, it's not drawn a message here from Q to R, which it's a mistake that we do. All right. Then we have a version with including a digital signature in the echo message. And this algorithm is also quite involved. And again, it's relying on digital signatures, and it's relying on a Byzantine quorum here that so many processes have replied. And this one, in comparison to this process that we looked on first, which was the authenticated echo broadcast. Here we are relying on we are relying on authenticated perfect links, which is relying on MAX. But in the signed echo broadcast, we are instead relying on, or in addition, relying on digital signatures. So if you saw in the first example, we had all-to-all communication step, whilst in, I wonder if but in this case we have instead of having the all-to-all communication step, which is something that scales poorly, we are just adding a signature whenever we have a large enough quorum, and by doing this we are able to remove or not have this all-to-all communication steps. So instead we have 3 phases where each phase is an O of n. So only in each phase there will be only n messages exchanged. So here process P is sending to all n processes, and they are all like attaching their signature and sending back to P, and then P is finally aggregating all these signatures together, and then sending this out once again. So you can see this sigma here. This is like the set of all the signatures that was he could aggregate together, and then all the receivers can check that. So this is like the step that all the processes do. That when they check that for all the processes that they know about, they can verify the signatures of so many messages in the set that it's over this const or this size here. So the Byzantine quorum. Yeah. All right. And by doing this, we do not need this step where we need to send the echo messages to all the processes. All right, so that was to send only one message. This consistent broadcast works by sending one message. And when we have the, so I guess I should change the title here also, because now we are talking about reliable broadcast. Something reliable broadcast. It's not so important to do right now, but now we now we extend what we had from before to ensure also agreement among the correct processes. So this is the totality property. If some message is delivered by any correct process, then every correct process eventually delivers a message. Here so I don't know if it's maybe not worth to go into too much details here together, all of us, because this is like those things that it's kind of useful for you to sit down by just yourself and try to reason about this algorithm. So if we start from the perhaps the figure, it's more easy to get started here. This is the name of the algorithm: authenticated double echo broadcast. So now we have 3 phases, and the first one is the initial send phase. It's sending the message to all the processes, and all of these processes are then replying back, plus they are replying to all the other processes. So it's like the first 2 phases. This is the same as we saw here in the stop to this authenticated echo broadcast, but now we are adding the totality property, meaning some agreement amongst the correct processes. Then we need another phase to do this agreement, and thus we have like the ready phase. And only once the process receives a sufficient number of ready messages, it will present reliable broadcast delivery. So there's 4 main things to know about here. This is, as I said, the sender is disseminating the message to all the processes. This is how it starts in the phase 1. The second phase is that all the processes are then echoing the message to all the different processes. Then once a Byzantine quorum of echoes is received, then ready is sent to all the processes again, and whenever you receive more than 2F ready messages, then you will deliver to the application. So all of these things, they are captured here in the algorithm. So it starts off with the first step, the broadcasting. So very easily just goes through all the processes in your system, sends the send, or triggers the send event. Then whenever we receive an echo, then we will no, excuse me, then whenever we receive a send message, we will respond back with a echo, and whenever we receive an echo, we will add it to our set of echoes received. And then we have we have 3 now conditional events that happens once a set is above some given size here. So the first one, it's whenever you have received a Byzantine, so remember this n plus f divided by 2, this is the Byzantine quorum, and this m is not equal to this nil value, so there exists an actual message, so that the number of processes that sent the echo for this message is above the Byzantine quorum. So in that case, there exist so many echoes, and you didn't already send a ready message, then you will send a ready message to all the processes. And when you receive a ready message, you do pretty much the same thing as you do for the echo, that you just add this thing to like an array, for example, or a dictionary, something that you just want to keep track of all the ready messages that you have received so far. And then when you have received more than F ready message, meaning that there must be at least one correct process among it must be at least one correct process that has sent a ready message for this message M. Then you will also send a ready message. So there's two type of events that it captures there, that it's possible that you will actually you will not send the echo message, but you will still receive enough ready messages so that you also are ready, or that maybe you lost some messages in the echo phase, but in the ready phase you received a sufficient amount of ready messages. And then if you have over 2F of these ready messages, so these two conditions here, they are the first lines here, they are the same, only that in the second case, when you have over 2F, so that you have a majority of correct processes, because remember that it might be F that are faulty in always, so that over 2F, it means that it must be at least one that's correct among these responses. And this is like that if, for example, all the faulty processes try to collaborate together to do something bad to your system, then if you have this strong predicate here, then only they cannot overthrow your system because there are not enough of them. And anyway, when you have received over 2F or 2F plus 1 ready messages, then you will deliver up the stack to the application. So it's not too difficult to read these algorithms if you really spend some time, and you can expect to see such algorithms in your project also, that it will be more it can be more difficult to follow, but just ask any questions if you need. Then the last, I think, abstractions that they have here that we will consider is the broadcast channel, and now we are no longer limited to sending only one message, as was with the abstractions that we saw previously, the Byzantine consistent broadcast, but now we have a Byzantine consistent broadcast channel that allows us to send multiple messages. So I think the new property to consider here. Let's see, I think it has the same property as before, only that it now has the added label L here, and this label it's again like what we saw with the vector clock or sequence number. So this is the ID behind this L, and the algorithm, it's short and sweet in the sense that it's just using multiple instances of this Byzantine consistent broadcast, and therefore we can just rely on all the properties that we discussed previously, and yeah, you initialize this thing if you a priori or beforehand you know what process will send the broadcast, and yeah, then whenever the application wants to send a broadcast message, you are choosing one of these instances that was created, and you're basically doing the whole algorithm that we discussed previously. And once under the Byzantine consistent broadcast algorithm terminates, then you increase your counter, and you set yourself ready again. So you need to finish one broadcasting message before you're allowed to continue to the next one. So so here they also have a reliable or Byzantine reliable broadcast channel, which again has this added thing of the agreement property. If some correct process delivers a message M with a label L and sender S, then every correct process eventually delivers message M with label L and S. So a different thing here with the consistent is that there's no agreement on messages delivered. So whenever you need agreement, then it should be reliable. So the algorithm is not discussed, and I think that's it. I think this is all slides that I didn't want to present. It's all slides. Yeah. So yeah. So anyway, that's that for Byzantine broadcasting abstractions. And is there any questions regarding this? Because this concludes the chapter 3, and now we are ready to go into the most interesting parts of this course, maybe. Oh, I shouldn't say that, but now we can start to go into consensus algorithms, where we will use these things we have seen now with broadcasting and failure detectors and timing, vector clocks, and these things. So I think I updated the lecture plan, and if there's no strong objections, I was planning to not have a lecture next Monday, because I know that you also have the deadline of the lab 2 on this Monday. So this is just a few days from now. And then on Thursday, I wanted to have the whole Thursday for Paxos, which is what you will be asked to implement in lab 4 and 5 and so on. Yes, so I will try to share some information about Paxos beforehand, so that maybe you can read a little bit about it before the lecture. But Paxos, this is one, let's say, family of consensus algorithms, because there are many derived consensus algorithm from the original Paxos consensus. But yeah, I had planned to discuss this first, and then afterwards go into the consensus variants they have in the book. And currently, this is my plan for the project is to make you evaluate the research papers in relation to this Paxos. So I recommend that you follow along with this. Yeah, and with regards to the slides, they will not be uploaded, because I checked around, and since I'm using directly the images from the book, or the algorithms from the book, it will just be a whole mess for me if I sort of distribute this book. So what I recommend you to do is that you can get this book for free on campus, and then you can get or watch the video on YouTube. And yes, please, if there's any questions about any of these algorithms or abstractions or something like that, I can explain it again in if you want. Yeah, so that's that. So yeah, on Monday we will, because we are already according to the plan, we are finished now with Reliable Podcast, and yeah, I think that we can do a longer lecture on Thursday to try to explain everything regarding Paxos, but yeah, I will for sure share some research or some papers that explains this, so you can try to look on it beforehand. Okay, if there's no more questions, then we will continue in a week, and please remember the deadline for lab 2, so that we don't fall behind on labs. And also you should try to find a partner for lab 3 already now, because it will be a group lab, and yeah, all of the other labs will be group labs. So we want you to work in pairs of 2, and If you strongly prefer to work alone, that's fine also, but it will be some more work for you. Okay, then I will end here, and we will meet again on Thursday.